All right, so for those of you who missed class today because you were in Washington, D.C., I am going to redo the half Atwood derivation from yesterday as a recap. So I've drawn the half Atwood on the top left of the paper. This is a half Atwood machine. I've labeled the block sitting on the table, which I'm going to color in green. I've labeled it capital M, so the table block is large M and the hanging block is lowercase m, and we're going to ignore friction. So we expect that when we drop, if we were to hold on to this thing and then suddenly let it go, we expect that the whole thing would accelerate. So the block on the table would accelerate to the right and the hanging block would accelerate down towards the ground. And we talked in class a little bit about how that means we have a curved coordinate axis, which I did a very bad job of drawing, but that's okay. So the coordinate system follows the string around the pulley. So the positive x direction for the hanging block, the lowercase one, is down towards the floor, and the positive x direction for the block on the table is to the right. So if we want to know the acceleration, we usually start by making free body diagrams and Newton's second law equations. So let's work on that. Find acceleration for each block. Okay, so we're going to do free body diagrams, and we're going to do Newton's second law equations. All right, so for the block on the table, I'm going to draw a little circle around it and look to see what's going on. So here's my circle. It has a force up on the block from the table. That's a normal force. It has a force down on the block from the earth, the gravitational force, and it has a force to the right from the string. I'm going to call that a string. So it's a tension force from the string on the block, and that's what it has. And remember, it has, we defined the coordinate system, so the plus x direction is to the right. Sillily, you could also say the plus y direction is up. Very silly. So plus y follows, and it curves. So the plus y axis for this thing is going to be like this. Okay, so if we write Newton's second law equations, we have the sum of the forces in the vertical direction equals the mass of the object times acceleration in the vertical direction. And in this case, we don't expect there to be any acceleration in the vertical direction, which tells us that the force up from the table minus the force down from the earth had better balance. That seems kind of straightforward. And in the x direction, we have only one force, and that is the force of the string on the mass. That's in the positive x direction. Okay, so that's our main, most interesting equation. And I'm going to shrink these just so that they're not in the way. Let's do this. Okay. All right, so for the hanging block, little m, we have only two forces acting on it. We have the force of the earth on that block, and we have the tension force up on that block. We expect that's a little bit shorter because we do think this block is probably going to accelerate down. And let's put the coordinate system in. So we have this coordinate system, that's plus x. All right, so for this one, our Newton's second law equation would be positive. Well, let's write it out. The net force in the x direction equals the mass of the little block times its acceleration. And And we have two forces in the x direction. We have the force from the earth on the little block minus the tension force from the string. And that gives us this Newton's second law equation. So again, I'm going to make it little. Okay, so we have two equations. We're going to highlight them, this one and this one. All right, so what do we know? We know that the tension force on both sides of the rope is equal. So we can say that the tension force from the string on the sitting mass should have the same strength as the tension force from the string on the hanging mass, and so we're just going to call that Ft. We also know that the two blocks should have the same acceleration. And I'm having trouble spelling. So the acceleration of the little block in the x direction should be the same as the acceleration of the big block in the x direction, and we're just going to call that A. Okay, so let's make these substitutions and then see about solving for the acceleration. So for big block, we have the tension force equals the mass times the acceleration. For the little block, we have the weight of the little block minus the tension force equals. So we have these two equations. These are systems of linear equations. So we can solve with elimination or substitution. In this case, I think elimination is going to be easier. So I'm just going to add the two together. I add the top equation to the bottom equation, and I get the gravitational force from the Earth on the hanging mass equals, because we have one positive tension force and we're adding it to a negative tension force, and those two things add up to 0. So we have the two accelerations that add together. I now finally solve for the acceleration. So I'm going to factor out the acceleration on the right-hand side, and then I'm going to divide both sides by that. So I end up with the gravitational force divided by the total mass equals the acceleration of the system. Okay, and then just one last thing. We know that the gravitational force from the Earth on the little mass is equal to the little mass times the gravitational force constant, and then this is all divided by these. Okay, so that's another way of deriving the half Atwood acceleration. Now we can play these fun games to check our answer. This is our answer here. I wish I could make little firework things that explode on the paper. We're going to play this game, what happens if. Okay, so ideally, so this has a fancy name. These are limiting cases. And AP, this is why you really want the symbolic solution, because you can check it more easily. Okay, so what happens if the mass of the hanging mass is 0? Let's pull that picture down and see. Can I copy this? Maybe. I think I can. Let's put this picture down here. Okay, so what happens if the hanging mass equals 0? What do you think? If the hanging mass equals 0, the big mass won't accelerate. That's what we think will happen. So let's look at the equation. If we plug in m equals 0, we have 0 over m equals acceleration. That is indeed equal to 0, so that agrees with what we expect. Okay, that makes sense. What if the table mass were really huge? So now we're talking like giant elephant on the table compared to a little tiny hanging mass. We probably think that nothing accelerates, right? So let's check that out. We'd have mg, so the numerator stays the same, but you have basically infinity plus m in the denominator. Something divided by infinity is basically 0, so this would tell us the acceleration would be 0, and that makes sense. Okay, so that makes sense. And then we have one more we can do. We can say what happens if the big one, the table mass is 0. So these are our tests. What happens if the table mass is 0? If we make the table mass 0, then the hanging mass is just free falling. It has nothing to slow it down. So when we can check. And that would be down, so in the positive direction. So let's check. So we have mg over 0 plus m equals g. And remember, g is 9.8 newtons per kilogram, but that's the same thing as meters per second squared, and that would equal our acceleration. So it's positive, and we said down was positive, so that also works. Okay, so every test we can think of, this equation makes sense. And so this is definitely a reasonable answer for the half Atwood machine.